So students will recall the Wronskian that we talked about a little while ago. Here are the things we know about the Wronskian. Our basic fact about the Wronskian is that if the Wronskian is non-zero, ever, any value of x, doesn't matter what the value of x is, any non-zero value for the Wronskian, and it follows that that list is an independent list. So this is our basic tool concerning the Wronskian. Now, there's a temptation. Students very often misunderstand and think that it goes both ways, and would assume then that if the Wronskian were always zero, well, if that weren't true, then it would seem that that wouldn't be true, and therefore it would seem to follow that the list would be dependent. But that doesn't work. The mere fact that we cannot conclude independence does not mean that the list is dependent. So it's important to realize that this is false. Now, this is just a reminder of one of these properties of the Wronskian we talked about a while ago. Okay, now there's a fix for this, and under an additional condition, if you know that all of the functions are analytic, then it does work. But without that additional knowledge, it does not. Okay. So it turns out there's some other additional information that would allow us to sort of recover this theorem. And it has to do with these homogeneous linear differential equations. And here it is. Suppose you have a list of functions. I'm interested in the Wronskian, trying to decide if this list of functions is independent or dependent. And suppose now that what we know about these functions is that they are solutions to a certain linear homogeneous differential equation. Importantly, note homogeneous. Okay. Now, importantly, we do have to make some other assumptions. It's important that this differential equation satisfy the conditions of the existence and uniqueness theorem. So the coefficient functions have to be continuous, and the lead coefficient can't be zero, and etc. Of course, it's homogeneous, so the right side is clearly continuous. The other thing is, and this is also very important, it's very important that the differential equation be an nth order differential equation, n being the number of functions that you're talking about. So if you're interested in the list of 5 functions, they have to all be solutions to the same 5th order differential equation. Okay, so there's quite a few conditions that have to be checked. But that being said, if you have a list of functions, satisfy these rules, Wronskian 0 does imply that the list is dependent. So again, it's kind of a fix of this would-be, the false but wishful thinking that we saw previously. Okay. Now, in fact, this is even more than that. You'll notice that says, what we were previously considering was the case for the Wronskian is 0 for all values of x. This is importantly different. This does not require, for this theorem to work, we do not need to check that the Wronskian is 0 for all values of x. It's good enough simply for the Wronskian to be 0 at any value of x, any value at all. And that alone, along with these conditions, allows us to conclude that the list of functions is dependent. So this is a really powerful result. Arguably much more powerful than the result, depends on how you look at it, that we came up with concerning analytic functions. Okay, so let's see why this is true, and it's an instructive proof. So keep in mind, we're assuming the Wronskian is 0 for some value of x. Call it x naught. Okay. Well, what that means, don't forget what the Wronskian is. It's a determinant. It's a determinant of a certain matrix of coefficients. And those coefficients are these numbers here. All right, so there's this matrix of these coefficients, and that determinant is equal to 0. That's what it means for the Wronskian to be equal to 0. Specifically, again, notice we're talking about at a single value x naught. Right, we're not making a general statement about all values of x. This is only known to be true at a single value x naught. Okay, fine. So these coefficients with their determinant of the matrix they form being 0, we know that there is a non-trivial solution, namely that there are coefficients C1 through Cn that make this work, specifically non-trivial. Okay, so there is some way to make this system work. And what we're going to do now is consider the function that you make up out of those coefficients. So we're going to take those same coefficients and use this to define a function of x. And very importantly, notice that this is a function of x. This could be any value of x, any value of x at all. We're not restricting our attention now only to x naught, that same x naught. We're saying that this is true for all values of x. So this is a function called u that's defined for all values of x. Okay. All right, so now what can we say about this function? Well, here's a free thing that we can say about this, and this is cheap. But this function, there it is. So we know that when x is equal to x naught, this function is equal to 0. Okay, so that's sort of a preview. You might say we set it up that way. But here's the other thing. This actually tells us something as well. That is exactly the expression that you would get from this by taking the n-1th derivative and plugging in x naught. So this function u, not only do I know that its value at x naught is equal to 0, but similarly, the derivative is relevant to this system of equations. So the derivative of u at x naught is equal to 0, and et cetera, et cetera. And the nth derivative at x naught also equal to 0. This function u, we know a bunch of information about what's happening to that function at this value x naught. And let's write those things down. Here it is. U has the feature that its value and its various derivatives at the point x naught by way of this system of equations here are all equal to 0. Okay. All right, now we know another thing about this u. It's a linear combination of solutions to a homogeneous differential equation. Well, if these are solutions to a homogeneous differential equation, so is the linear combination of them. So I know a lot of information about this u function, as it turns out. In fact, knowing as I do that it's a solution to that homogeneous differential equation, knowing as I do that it has these values, it therefore satisfies these initial conditions, and therefore, altogether, I know that this function u is the solution to this initial value problem. And don't forget, initial value problems, certain conditions being satisfied, which by assumption in this case are, solutions to initial value problems are unique. So, one way to say, all of this, sort of summarize what I know about this function u, is that it is the unique solution to this initial value problem. Yeah. But wait a second, this initial value problem, there's an obvious solution to this initial value problem. An easy function that I can plug in. A function y that starts at 0, the derivative is 0, all of its derivatives are 0, and L of it is equal to 0. And namely, that obvious solution is 0. Let me 0. So u is a solution to this initial value problem as previously observed. 0 is a solution to that initial value problem by casual inspection, but the solution is unique. And therefore, the u function that we wrote down is actually equal to the 0 function. Now keep in mind, u is defined to be this. That means that we have a linear combination of these y functions that equals the 0 function, and that means that this list is dependent. Okay, so it's a wonderful proof. I'd like to make a quick observation about what made this proof possible. Really, the big tool here was the existence and uniqueness theorem. Right? We wrote down this function, and initially all we knew about it was what we could say about it at x naught. Only at x naught did we, based on the givens, immediately really know something about this function. But because of the existence and uniqueness theorem, we could draw the conclusion that this function doesn't just behave like 0 at that one point, it also is 0 exclusively, identically. Okay, so again, it's the existence and uniqueness theorem that allows us to make that huge leap there to draw this conclusion. Okay. All right, so there's a really nice corollary of this, and that is that if you have a list of solutions to one of these homogeneous linear differential equations, nth order satisfying the conditions of the existence and uniqueness theorem, so all the usual conditions. So solutions to a differential equation, then very nicely, there's only two possible cases. Either the Wronskian is always 0 and the list is dependent, or the Wronskian is never 0 and the functions are independent. These are the only two possible cases. Now, certainly, if the Wronskian is never 0, well, then it immediately follows that the Wronskian is sometimes non-zero, and sometimes non-zero immediately gives you independent. So this case is an easy one to understand. Likewise, this case here, not so bad. If the Wronskian is always 0, well, then by the theorem that we just proved, we get that the list is dependent. So the individual two cases are not hard to understand. The tricky part about this theorem is how do we know that there isn't this third case? One would think that there's a third possibility, which is that the Wronskian is sometimes 0. And what would that mean? And why is that not listed as one of these cases? What if the Wronskian is sometimes 0? Well, the thing is the theorem we just proved actually addresses that. The theorem we just proved does not require that the Wronskian be always 0. It simply requires that the Wronskian be sometimes 0. That's what this says. Just for any value of x naught, just pick a value, any value. As long as it is ever non-zero, as long as it is ever 0, then I get to conclude this dependence. So going back to where we had been, this condition, this seeming third possibility of the Wronskian being sometimes 0, the theorem we just proved show that that would mean dependent. But we've already shown long ago that if a list is dependent, then the Wronskian is always 0. In fact, this is really the first thing we ever proved about the Wronskian. We assumed we had a dependent list. We showed the Wronskian would have to be 0. So this seeming third possibility of Wronskian being sometimes 0, it's not possible, because if it were ever 0, it would have to be always 0. So therefore, these are the only two possibilities. And let's see an example. Well, let's see here. We don't have an example. Okay, we'll see an example soon.